now. So, yeah, welcome everyone again to this session of the AMATIC Midwest Region Math Bonanza. And our website is amatic.org/Midwest, but I will send a link to that out again after the session once all of the resources and recordings and everything like that are posted. So I am going to pass it over to our presenter, Chris, to have him introduce himself and whatever else that he has to say before starting. And I know that I have some exciting links in the email somewhere that I'll be putting in the chat at appropriate times. And if I missed your biography, Chris, I apologize, but otherwise I will just turn it over to you.
No, I did not send you a biography. I'm at Oklahoma City Community College. I've been here 23 years, and but I'm supposed to be in Budapest. You can see on my background. I was supposed to be there working with Budapest Semesters in Math Education. I've been working with them virtually. They did do their summer program online, but I'm pining for my summer in Budapest. About 10 years ago or so, at the joint math meetings, I went to a pre-meetings workshop that was put on by a group of statisticians from Cal Poly San Luis Obispo, Alan Rossman, Beth Chance, Roxy Peck, and they started introducing the idea of teaching statistics, especially inferential and probability concepts, by simulation and hands-on activities to try to help students understand the concepts more, especially as a lot of the computation should be moving to being more automated. And so I've used some of their activities, even used their textbook for a while, and have thought about and looked for other things and ways to expand on this. So the reason I try to use more hands-on stuff in stats than do a lot of lecture over the concepts, first of all, it gives me an opportunity to force students themselves to work on their fraction, decimal, and percent skills, which even in a gateway math course, or what for some students is a support math course after they've had some other 1000 level math course, fractions, percents, decimals are still issues. And we hear that those are issues from our science colleagues as well. Especially then in their science classes when you throw in things like scientific notation and significant figures. So anytime I can get students to practice using fractions, percents, and converting, I do. Turning a statistical case study into kind of a game can engage students a little better if they're thinking of it as they're trying to achieve something. And especially if they're in groups, sometimes they get competitive with each other, even though it's all random. And then taking how winning the game or achieving the desired outcome can then translate to how we would ultimately do some real statistical or probabilistic analysis. A lot of times we're doing these simulations before we've introduced the actual concept. So the concept is being built through the simulation. And then they can also see, either by a hands-on or a computer simulation, how these sampling distributions build. And with some of the applets especially, they can see how the distribution changes as they add more samples or add more trials. So the first one I want to show y'all. And I typically do this one early in the class. Maybe we've talked a little bit about basic probability. I might have introduced the concept of the binomial distribution, but in some cases not. Maybe just we've done the ideas of basic probability and what an expected value might be. So we've got a 36 multiple choice question, each question with 4 possible answers, and we have a student, and students do this all the time. They figure, hey, I've got a C. To keep my C, I only need to make 40% on the final. I'm not going to study much. I figure I can get a 40 just by guessing. So that's what the student is going to try to do. And that's what we're going to try to simulate. So some preliminary questions I'm going to give the students, which will help them then set up or understand what the simulation is going to be. What's the % chance of guessing the correct answer? And then how many of the 36 questions does the student have to answer correctly to get at least 40%? I deliberately choose something so that when they do that 40%, they don't get a whole number, and they have to think about whether they should round, whether they should cut off or truncate, or whether they need to round up no matter what, right? These are questions, again, that translate well to their science classes, because depending on context of what they're calculating, especially from their lab data in science classes, sometimes they're just asked to truncate. Sometimes they don't use regular rounding rules. They use science rounding rules. So they have to think about it. In this case, the student's going to have to get at least 15 right, because they can't get 14.4. This class does not give partial credit on the multiple choice questions, right? So they have to think about these to get ready. So now here's what we're going to do. One of my colleagues, who has since retired, bought a lot or requisitioned and had the department buy a lot of manipulative stuff, mostly for our Math for Liberal Arts course, but I use it a lot with our statistics course. So we've got all the dice sets with all the different sided die. So I pull out the 4-sided die, and I randomly chose rolling a 2 being equivalent to winning or getting that question right. Sometimes the students ask, they think there's some significance to whatever number I choose. And that's a good way to then turn it back around on them and ask them, well, does it have significance? I'm very good at, a group calls me over, why is it a 2? And I will look at them and say, why is it a 2? And just walk away, right? Leave it to them and then come back. So they're going to roll the 4-sided die 36 times. So they're representing each simulation, each question. Normally they're going to be in pairs or maybe groups of 3. If a student really wants to work by themselves, I'll let them for this. A lot of times they want to have at least one student rolling and one student recording. And I tell them, in whatever allotted time I give them, repeat the experiment as many times as possible. Some groups will get 3 to 5 trials done. Other groups will work very fast and get 10, right? So again, the competitive aspect of the game comes in. So I want them to record how many times their student wins and how many actual times they roll a 2 in their 4-sided die. So winning means they get at least the 15 out of the 36 correct. Then we write it all down on the board. We write the actual results and then how many times they win, so that the whole class can see it. And then we start adding things up and we can start asking questions about the results and what the distribution looks like. When I first started this, I had tried to get them to go up and graph it in some sort of dot plot. Then I found they were putting things in the wrong places. So I just have them write the numbers on the board and we can create the dot plot or histogram, whatever we want later. So questions. What percentage of the time did the students guessing the simulation win? So of all of the trials that got reported on the board, how many times did the student get at least 15 out of the 36 questions correct, and turn that into a percentage. I deliberately don't tell them where to round off that percentage. So then we can talk about what you want to report, how accurate you want to report it. In this case, it's informal. So you might not want to go too many decimal places out. Maybe nearest percentage is good enough. Then I change it and say, okay, well, what if it wasn't 40% for the win? What if the student only needed 33, 34% on the final? What percentage of the time did that happen? And they can see that percentage. And sometimes I'll ask more than just those two. So we do that as a class, and we make sure we've all got the same answers and all on the same page. So then follow-up questions, either that I have them do in their groups, or I might have these posted as a quiz or a homework on the learning management system, especially if I want them to write some stuff. I might let them hold it for later and think about it. And again, most of the time I'm doing this, we haven't talked about statistical inference formally, so we haven't talked about a p-value or confidence intervals or things like that. I just want their sense of things. Is it likely or unusual by pure guessing for the student to get that 40%? And I don't care which answer they give me, I'm more interested in their explanation. Normally when I give a writing exercise like this, I will grade it and give them a chance to rewrite. Most of the rewriting has nothing to do with numerical answers. It has to do with how they communicated. Improper use of vocabulary, poor, really, really poor sentence structure, things like that. Trying to work on their communication skills as well as their statistical understanding. Right? This one I've had a lot of fun getting weird answers to. Why does this simulation really not accurately reflect a student guessing? Because I don't think it really accurately reflects, because students will come to a test with some knowledge, right? They're going to be educated guesses, not random guesses, unless they decide they're just going to draw a picture with their dots on their Scantron sheet. So we have a discussion about that. And so, okay, it's not accurate. If we had a more accurate simulation, what happens to the chances of the student winning? So I build some discussion questions, and we can start thinking about how probability works. Number 3 can lead you into some conditional probability if you wanted to go that deep into it. In our statistics class, we try to stay away from a lot of complicated probability rules so that we can get to the statistical inference quicker. But if you were teaching a class with a more probability emphasis, then you could really talk about, hey, how would we build an actual simulation? Maybe if you had a course, a probability and statistics course with math and computer science majors, a more upper level course. Now you can start talking about programming themselves. How would they do a good simulation? So after we do the hands-on, then I move to either in class, if I have a long class and we go to the computer lab, or as homework, or maybe as preparation work for the next class using applets. Why would I want to use applets? You can change the parameters quickly. Normally they're sliders or just buttons they can toggle. They can see how the results change continuously as they run more trials. They get instant results. And after I give them assignment, I can add one more piece to it that says, hey, change the settings to whatever you want. See what happens. Do that a couple of times and just report what you observed. So there's some free play involved. They can do their own investigation. Some things that I always worry about and check on when I'm using applets is I'm using them to supplement. They still need to refer to the actual text or the actual videos or my actual supplementary notes. The applet is not the teaching tool. It's a vehicle to help them develop the concept, but it doesn't have all the definitions and formulas, right? When I give an activity, you've got to give very detailed instructions. We think our students are good with technology. They're good with technology when they want to be. If it's something unfamiliar to them, they're going to click the wrong buttons. They're going to put the wrong numbers in the wrong places, and they're going to get very skewed results. I'm also aware, and we should all be aware, that the concept I might think they're supposed to learn by playing with the applet is not the concept they're going to see. They're going to see other things. Sometimes those other things are legitimate and valid. Sometimes they're way off base. So you have to be prepared when you bring all the students back together that weird things are going to happen and weird things are going to be reported. The other thing is there are still applets out there that are programmed in Java and Flash. Flash you can still make work. Most of the Java applets are going to give your students all sorts of security warnings. If you're using your on-campus computers or tablets in the classroom, students may not have permission to allow those applets to run, especially if they're Java. So I'm continually checking things and making sure they run. Most good ones have transitioned or are transitioning to JavaScript or something even more accessible. I don't just do complete free play because, like I said, the students aren't good with technology. Some of the applets are not intuitive on their own. Sometimes I'm doing this with students that are unfamiliar yet with the vocabulary, and students don't know what reasonable values are for some of the parameters. So I need to guide them and direct them a little bit. So this is one, and we're going to get to play with this one a little bit in just a second. This is for one proportion inference or building binomials. So you put in the theoretical probability of success and the sample size, the number of samples you want to run. You can either track number of successes or proportion of successes and calculate your probabilities or your proportions from your samples from there. You can also add in calculating the exact binomial or the normal approximation p-value. In the example that I'm using this for, that case study, we have what would be considered a small sample. We have a sample size of 36 and a theoretical probability of success 25%. So by most standards in the textbooks that we use, I only have an expected number of successes that is less than 10. So when you look at the exact binomial and the normal approximation, they're off from each other. You don't get nice convergence, even with a large number of samples. So then there's an end to talk about some of those sample size assumptions and what do you do when they're not met, which is a good reason for teaching the exact binomial. Not by hand. I'm not teaching intro stat students to sum a bunch of combination formulas, but to talk about the difference and when they converge and when they don't. So we're going to look at this and you're going to get to play with it. So just to go through what we're going to do, the probability of success, the sample size, we're going to start with 10 samples. If you want to see the animations, you can. They tend to slow the simulation down. Turn summary stats on so you can see the mean and standard deviation, and set the number of successes to be as extreme as greater than or equal to 15. So the way I do this with my students, they draw 10 samples. They see a nice little dot plot. It might start to look normal, probably not. Then I add 90 more. Then I add 900 more. Then I add 9,000 more. So each time they do it, we're adding more and more samples. They can see what happens to the sampling distribution and see what happens to the mean and standard deviation of that sampling distribution. So John, if you would, I'm going to stop sharing for just a second. John has put in the link to that applet. And we should be able to put people in breakout rooms, and one person kind of take charge in each breakout room, running and share your screen and run the applet. You can use the settings for our case study. If you want to use others, you can play around with other settings and see what happens. I'm going to send y'all off for a few minutes to play with the applet. John, if you would, send people off to breakout rooms. If John is here, there he is.
Oh, I can't hear you.
Good. How are you?
Oh, there, I can hear you now.
Okay.
Let's see. Yeah, let's see. I have to be the one to apparently figure out how long we have, but that's okay. So I probably shouldn't be the one to share my screen, since I can't even figure that part out, but or maybe I can. I doesn't.
Yeah. That'd be great if you can. I don't know what we're supposed to run an applet or something, or you're running
Yeah,
it?
I have it up. Oh, good, John.
I manage, I think.
Okay.
So, I mean, I did the one in his slide, but I'm not sure. Well, I'm not sure exactly what he wanted us to do. I missed that part when I was trying to find the link. So, I mean, I think that this is good, because what I don't usually do the spinners. I usually do the where is it, oh boy, like the coins, but I mean, I'm sure that the spinners are just as good. I really don't even know how to get back to the coins.
April, had you used this before?
No, I haven't. So I guess, oh, here it is. Here, I had to refresh it, but here are coins. So I guess.
Yeah, I've never used this. I tutor, but I've never taught this, so I've never even seen this before. This is kind of nice.
Yeah, I mean, I do like that though. Like like, I'm really not sure though, like how, like, I'm not really sure, like, I guess five tosses isn't enough, but I mean, now that I have this up, I mean, I can enter whatever number both of you want to see.
Okay, yeah. So wait, so you did, because I can't, it's real small, but so you tossed the coins 5 times, you said?
Yes.
Okay.
Oh, number of repetitions. How about like 50? Okay, maybe that's 50 repetitions. That might be more of what we want. So
Okay.
I think that at 50 repetitions, it doesn't look like that reached the normal distribution yet. Maybe at 100, maybe a little bit better. Maybe like 1,000.
Huh.
Yeah, I mean, I guess at 1,000 that's pretty good, because you don't have like a really big like one of the spikes bigger in the middle, and then 10,000. Yeah, so like 10,000 is even better, I guess, but
Huh.
and I guess if you go by the number of heads, then at that point, like 2 or 3 heads looks like what you would get out of on like between 2 and 3 on average for each of the 10,000, which is, I guess, what I would tell my students to sort of go about doing. Like if I would probably tell my students exactly that, like put in like 10, put in 100, put in 1,000, put in 10,000, and then see like how many does it take for it to the data to be close to a normal approximation of a curve here. But I mean, that's, I guess, the best we can do in a online setting. I mean, my students actually like really think this is ridiculous when we do it in class, because I have them sit there and flip their coin thousands of times, but it is what it is. I mean, they sort of realize after that sometimes we want to know the exact calculation, because we don't want to have to sit and do everything by simulation.
Right.
Yeah, I like the idea that you can play around with it like that and see how it immediately how it affects the graph.
Yeah. I'm going to go and like sort of spy on the other groups and see if it seems like Chris is done with the breakout rooms yet or not. So
Okay.
so
Yeah,
if
he
I
didn't
hear,
give it
that's
the
why.
time.
Cast the class.
Yeah.
Right.
Well, and I mean also in general in probability, we know with the more continuous a function is, the probability of an exact event is 0 anyway. So
Right.
Synchronous where they need to be synchronous and identify what could be moved.
Yeah, so this is something I would definitely give as kind of a class preparation assignment for an online, for a hybrid. And then as maybe a preliminary assignment in an online before then they watched the videos and did the actual lesson on binomials and hypothesis tests for one proportion.
It's a lot of
All right.
stuff to
So everyone else was still playing or trying to figure it out because they didn't have me in there with them.
I'll be honest, it wasn't until right now that I realized you could leave a breakout room early, so I didn't realize that was possible.
You can always leave a breakout room.
Really?
Yeah.
Is it just
You just come back to the main, you just come back to the main session and sit there and, you know, either by yourself or with the host.
Interesting. Yeah,
Well,
I gotta.
Yeah, and the
breakout
host
rooms
go
better.
in and spy on all the breakout rooms too.
Yes. And that is something I do frequently.
That seems like
when
that
I'm
would be
teaching this way. I students like that instead of waiting for them to raise their hand. All right, so there's one question. Is everyone back, John? Or are we still?
I think everyone who wants to be back is, as far as I can tell.
Okay. There was one question, you know, doing this in kind of an asynchronous environment. I do that. I teach this course in hybrid and online formats. And so I would give this applet exploration assignment as either a class preparation assignment for the hybrid or as a precursor online to the actual lesson on binomial variables and hypothesis testing for one proportion. Whereas with the fully face-to-face class, I'd probably at least get the students started on it while we were in class, either in the computer lab or if enough of them had laptops or good enough graphics on their smartphone or tablet, do it in class first, at least at least to show them how to use it before I let them go. So go back to where we were. So things I would, in general, ask them about applets. What patterns do they notice as they increase the number of trials? What changed? What stayed the same? You know, what happened to proportions of success and failure? Some of the applets will fit the theoretical distribution curve over their histograms or dot plots. So if I have an applet that does that, I'll ask them about the fit. And then ultimately we'll ask them, you know, how does this applet reflect this concept or principle that we're trying to study? In this case, you know, what happens to the binomial distribution as you keep increasing trials? And what can you calculate, or what can you say about the probabilities? All right, this next one, I don't have a hands-on thing for. It's very difficult to come up with a hands-on simulation, at least from my perspective, for inference on one mean, because you have to find a population to sample from. You can do it with the computer. You can write little procedures, or actually you can just go find procedures that have been written in R or Python or other things, which can then sample as many times as you want from especially government websites that have a lot of data available, and the NCAA has made a lot of its data available as well, but there's nothing hands-on. If you have a case study that is a randomized experiment comparing two means, there are ways you can use cards and shuffle those cards where each card represents an individual in the clinical trial, and they just get re-randomized, and each card represents an individual and their results. And so it takes a lot more time because they have to reshuffle, and they have to look up every time what card corresponds to what quantitative value. But it can be done to simulate two samples with small sample sizes. This website, so up at the top, you would choose your distribution, and your choices are normal, skewed, uniform, and then there's this custom one. Then in the third place, you choose what statistic you want to follow. Typically, when we're doing quantitative data with the first statistics course, we're looking at means, and then your sample size. And this is one I was talking about. I can toggle that fit normal button so it can show the normal distribution. So I have them use this. We start the first time with a normal distribution, and in the middle set of buttons, they can choose the number of trials. So they first take 5 samples, and I have them keep adding samples in multiples of 5 till they get up to 50, and they can see how the sampling distribution changes. Then I have them add it in multiples of 10,000. So they get up to 50, 60,000 trials, and they can see how the sampling distribution starts to be approximated by the normal. They can also see how the mean and standard deviation change or not change accordingly. And again, I might not have shown them the actual formulas for how the standard deviation changes, but if they pay attention every time they add more samples and I ask them to look for patterns, they'll notice that the standard deviation that gets calculated is about 5 times less than the original population standard deviation. So if they're noticing that pattern, then they can start making the concept connection to the square root of the sample size. I say if they make the connection to the pattern. It's not always obvious to all these students, right? Some of these students, even though they've had multiple college level math courses, they're still very math anxious. they're waiting to be told what they're supposed to be looking for. So I think John has the link to the website, and this one has a lot of questions. This document on Google has the entire assignment. Let's see. Yep, John has shared both of those in the chat. So we're going to go back into breakout rooms, and we don't have to be in the same breakout rooms. We can re-randomize. Only work through the third part where you get to customize and draw your own distribution and get creative with the distribution you draw.
Oh, there we go. Oh.
So I couldn't get the link to work. I don't know what the heck I did.
Oh,
So
the link?
here's the chat again. So I don't know if I'm hitting the wrong one. I'm outside, obviously, so I'm having a hard time seeing my screen. Let me see if I can make it brighter. There we go. So which one? The one that is the Ross?
No, the online stat book.
Oh, online stat book. My bad.
Here,
I got it. Stephanie, are you way ahead of me again already?
No. I guess I'm ahead of you in the sense that I have successfully opened both of the documents.
Okay.
And now I guess I was kind of trying to pay attention while attempting to read and decide what I was going to do. And
I know it's hard to do two things at once. So John is helping us out here.
Yeah, I do like how this thing in particular has made me realize, in terms of my own teaching and whatnot, as soon as I get this link to this thing, I stop paying attention to what I'm supposed to do, and I just start fucking with
I know.
it.
Well, obviously, I know Chris. He already called me out for playing with stuff and not paying attention because he's seen me in action live.
I think it's natural.
I do too, and I think students probably do that as well.
I think they do.
Yeah, and that's why I was trying not to put it in the chat until the very last second.
That's a smart move.
But,
well, it's like when you hand a worksheet out in class, right? Then they start looking at it. They don't listen to you anymore. So it's the same. It's the same kind of thing. It's just kind of funny.
But I was trying to figure out what we're supposed to do. It said model 1, population is approximately normal and distributed.
Go to 3. He said go to 3.
Yeah, but has, mu is 16 and sigma is 5. So what do you expect to be at 25? So I'm not sure where I'm supposed to put that.
Well, so you've got a normal population. You've got that set up already. I think it's then down with that. Yeah, they're talking about the mean.
Or the...
Oh, I see. It's up at the, in the blue and pink up in the lower or upper left is actually telling us what the mean and the median are.
Oh, I wonder, but I thought that if it's supposed to be 16 and 5. Okay, I see. So you can't change that. Yeah,
I think that's just set.
Okay, so then what do you expect it to be for 25? So there's standard deviation 25, and then...
How do we actually do the thing? Well, oh, I see.
And then sample 5.
Oh.
So that's 5 times of 25, I guess. Oh, okay, let's just do 100,000.
Yeah.
So at 100,000, you expect the mean to be 16 in the standard deviation to be 4.85. So I guess that's not bad. Like it's close to 5. I guess I mean,
Yeah.
we can do another 100,000.
I
Or I
don't
did
actually think this one does
300,000.
another. I think it resets it every time.
No, actually it went up to
Oh no,
40.
yeah, you're right.
Yeah. So like I guess so this is 400,005 repetitions of 25. Like I think this is
Oh, I see what I'm doing wrong. I didn't change my
500,000,
sample size to be
600,000,
25.
700. I might as well just go for 1,000,000. I mean, we have a few seconds left anyway.
So you're talking to us and you close the breakout rooms at the same
Well,
time?
no, like actually, I had put a timer on the breakout room of 5 minutes.
Oh, you did. I don't think I've.
So that I wouldn't forget to close them.
So you can do that when you set up a breakout room?
Yeah, so like there were little options that said like, do you want the 1 minute timer to show? Do you want it to be a limit of 5 minutes, 10 minutes, whatever?
Oh.
So now I don't have to remember to close them.
Oh, so I have not done that because I used them all summer and I just put it on my watch for however long. And I was changing the time all the time, right? And then sometimes I would shoot them in there and I'd forget to start the timer because I would try to give them a head start before I started visiting them. And I'd be like, oh crap, you know.
Well,
I have no idea.
Yesterday.
I think was, can y'all hear me? Okay, my computer was telling me I was muted, so I got confused. That applet by itself, you know, when I say things about sometimes the applets are not intuitive, that is not one I would just send students to and say play, because even with that first instruction page, it's not intuitive to someone who doesn't understand statistics how it should be used. And I think I should even provide more instruction. This is one I really like to start in class with, or for an, I haven't used it in an online course. I mean, I have to this fall. So I think I'm going to make a video of myself playing with it, maybe with a uniform distribution before they play with it themselves. So I just want to stop for a second. What questions, comments does anyone have about anything right now?
You know, Chris, I made the comment that like, so the group I joined knows that I struggle because I didn't know that I couldn't change the mean and standard deviation from 16 and 5. So that might be one thing to maybe add that like I read the first question and thought that I had to type in the 16 and 5. So if you're planning to rewrite that for an online class, I might do that, because that's the first thing that I got confused on. Like, oh, I can't figure out where to type in the 16 and 5. So like once I got past that, like I realized I could do 1 million repetitions of 25 per sample quickly, and I sort of enjoyed it after that.
Yeah, yeah, like I said, this is one I've only been doing in class, and so I tend to walk around and make sure they all get it right. So yeah, thanks, John. All right, so back to it. Oops. All right, this one is a lot of fun. It introduces some basic ideas of probability, and the law of large numbers and expected values for random variables. The idea here, it's called Random Babies. It's built off the traditional problem for this was based on gentlemen going to the theater and they would check their hats at the cloakroom, and instead of taking their chit back at the end of the show and getting their hat, they simply walk up to the desk and are randomly given a hat. And the question was, what's the probability of however many out of the total number of gentlemen receiving the correct hat back? This is an updated version of this. The default setting is 4 babies. So the idea is there are 4 babies that have been born at this hospital, and they are randomly sent home. What's the probability of certain number of babies making it to the right house? What's the expected number of babies that will make it to the right house? So if you're doing a more probability-based course, you can actually write out all 24 permutations and then actually calculate these theoretical probabilities yourself. With my intro stat class, I don't have time to go into permutations that deeply. With my Math for Liberal Arts class, I do. So I use this applet with them as well. And I've actually run, you see 23 trials there. I ran one to start with and then the 23. And so the actual probabilities versus the expected ones are really close, even just after 24 trials. And my expected number of successes is almost exactly 1. And this dot plot here, or scatter plot, develops as the number of trials progresses. So students can see that develop. You can change the number of babies. Anything between 4 and 8 on this applet, it will show theoretical probabilities. Less than 4 or more than 8, you'll just see your proportions from your trials. You won't see the theoretical. So when I ask students to play with this on their own, I tell them, if you're going to set it at something different than 4, stay with 5 to 8 so you can compare with the theoreticals. So we're good. When I have them do it formally, we start with 4. Like I said, if you do 5, you start trying to list the permutations, you're going to spend too much time and you're going to miss some. There's a really cool animation with this. It's fun to see one time, but you don't want to see it over and over. Then you run the 23 more so you can compare it with the actual 24. I get my students to 200 total trials, but you can go more than that. And then I want them to, as they run those extra trials, I want them to watch that scatter plot in relationship to the expected or average value line to see how that how that develops. So again, yep, John has put the link to the applet. And I know I keep 2 out of the 3 applets I've shown you are from the Rossman Chance, Alan Rossman and Beth Chance at Cal Poly, just because they were the first ones who showed me these things, and so I tend to use theirs. There are tons of others out there. Rice University has a whole library of applets. People are starting to develop applets for Desmos and GeoGebra, which you can also then teach your students to program because they don't have to learn a language necessarily to do applets or dynamic things on Desmos and GeoGebra and other things. So, John, randomize this again, please.
The number of people in this.
Oops, I didn't hear you.
Yeah,
It could have been me.
likely is it?
Yeah, how likely is it that Julie and Stephanie keep getting grouped together? How likely is it, John? Oh yeah, let's look at the.
Well, yeah, I just brought it up
The
because
animation
I
is pretty
didn't really
great.
follow
Is it?
things
Is
because I
it pretty
wasn't
good?
I like
paying
it.
attention. So, like, do I put the
Show theoretical. Yeah.
put
Yeah.
this is where I put 1?
Yep.
Oh, well, then, well,
Oh, they're all
boy.
sad. Nobody got their own baby back.
They're all sad.
well, Oh boy.
Oh boy.
So then he was saying after that, unclick animate, so we're gonna have to watch that 23 times, and then yeah.
Oh, then type it in. I
Yeah.
did 20. I did 2 already, right? So 23 more times. Oh well.
Oh, we have some happy people, huh?
I mean, yes.
Some happy.
Holy cow! One time, all of them got their own baby.
Did they?
Yeah, that would be what number of factors 4 means, right?
Yeah. So 2. Yeah, 2.
Oh yeah.
Oh yeah, I could look at that instead of trying to estimate it off the
So like
histogram.
I know, right? I didn't look up there either. I'm like, oh, the graphics.
Pictures, man.
Show me the graph.
This is
I
why
feel
data
like,
visualization
so
is so
then,
important.
wait, what, 76? Wait, no, how many more times? 75 more times, maybe? Or
He had a big
105?
list.
I don't know. All right.
I don't
so,
know. Oh, you see the happy sons, and then they go away again.
So, like, this is interesting because, well, I feel like a student would automatically, like, ask, like, why is 3 matches 0?
It is.
Which I think that those are sort of things that I think would bring up a lot of discussion.
That would be definitely a good discussion about the like theoretical underpinnings.
Oh,
Yeah.
what does relative frequency do?
I think yeah, I was trying to figure that out, but then you guys were having an interesting conversation. Oh, I think you're just looking at the,
Oh,
yeah, it's the p hat for each.
oh, I see. Yep.
Oh, yeah.
Oh, versus the average of.
Yeah. I mean, true confessions, I don't teach stats. I taught it one time in my 29-year career. I do teach quantitative reasoning though, and I know Chris, so that's why I wanted to come today because I know he's always got good stuff.
Yeah, like actually I thought about this, and I like he asked me like what topic do you want me to talk about, and I said, well, we don't have any other statistics presentation, so do something about statistics. So this is what he came up with. But,
There you go.
but I feel like this is especially important now because I can see myself sending students to the applets and telling them to do things, or even like post their results in the discussion forum and talk about how their results compare to someone else's, or I mean there could be lots of different things that they come up with, but I mean I wonder if I do like 800 more. I really want to see this.
It's gonna take a while to do, but yeah, it is a good demonstration of the more trials, the more everything expected approaches
Right.
the theoretical.
9,000.
I regularly teach statistics, but I don't have like a real great statistics background. I feel like specifically probability. I mean, you know, like I took like 2 courses, and I'm a mathematician, so it's not like I have no experience. Like especially the basis of probability, I'm like, I definitely know more than the students, but maybe not as much as I should know.
Yeah. I'm better at the probability part, probably just because I teach math for elementary school teachers as well. And a little bit unit in that, and then we have it in quantitative reasoning. And I did do a little bit when I taught high school too for a while. So there's a little bit more of a smattering in K-12.
Yeah. Yeah, but this is, I mean, I like the idea here though. I mean, I think that like this is like you can tell that this was like who this was built by, because this looks like a graph right out of like R or something like like that. So It sort of is probably what's running.
All right. I hope y'all had fun with that one. I hope you enjoyed the animation. Um, so Priscilla and I started talking that there is something that is a 24-sided die. It's fair. So I might have to incorporate that to simulate this with some dice rolling in class. All right. So questions I ask them, and that actually we discussed in our group. Why does it matter how many times I run this with whatever number of babies? One less than the total number of babies is always a 0 probability. For 1,000 level intro stat or math for liberal arts, quantitative reasoning type courses, that's a very difficult concept for students until you have them maybe actually sit down and try to draw a picture of the babies all going to the right place, and they're left with the one that has to go to the right house. You can, if you've shown them and done a little more deeper into random variables, they can actually calculate using the theoretical probabilities, the average or expected number themselves. And then ultimately the goal is, if I show them what the law of large numbers says, how does this applet, how does this simulation display that law of large numbers? What happens in the long run? And in Oklahoma, discussion of what happens in the long run tends to lead to a discussion of casinos and how the casino's long run is a lot bigger, a lot bigger than an individual's long run. And for the casinos to stay in business, it has to be that way. So we get into some discussion about, how casinos kind of keep you coming back. They let you in a little bit, but not enough. Because if you never win, no one's going to come and they go out of business. If they let you win too much, they pay out too much money and no one comes back. There are lots of others. I've seen people simulate confidence intervals for proportions, have a large tub with 2 colors of beads, and then somehow sample from the tub. It's nice if you can find a way to sample so you get the same sample size every time. There are some, I saw it once where there was like a spatula with 20 little holes in the spatula, and someone had found beads that fit those holes perfectly. So every time they could dip the spatula in, and students could draw out 20 beads and then create confidence intervals. And then if they do that enough times and the whole class is doing it, then you can show, hey, what does a 95% confidence interval really mean? And get beyond that 95% chance of something happening and move students towards understanding that 95%, that the randomness, the probability is about the sampling process, not the result. And to get them to understand that the true population parameter isn't what's random, because that's the big misconception. It's the true population parameter isn't moving around like whack-a-mole, right? It's staying in the same place. We're casting the net, trying to see if our net finds it. That's one of the very counterintuitive things about confidence intervals. It's technical. In the end, it doesn't really matter, but if students don't really understand it and they start doing their own statistical studies later in their academic career, it can lead to some of the poor interpretations that all of us see when things are reported. Other things, and I haven't done this with statistics a lot yet, but I mentioned Desmos and GeoGebra. Desmos is starting to build up, either in its own library, or people are creating libraries of sequences of commands so that you can do some statistical things. Desmos is already much better at doing regression lines and regression curves, even nonlinear things, than any graphing calculator, because it does it instantly. You just have to type in the general form of the curve you want it to try to fit the data to, and it does it. What I would like to figure out how to do on Desmos without making it too complicated is for that regression line also add confidence intervals for the mean response and prediction, without it again being too complicated. Those formulas are complicated to start with, but that's something I'd like to investigate. The other thing I've thought about, and I haven't done this, again, time constraints hit all of us. And lots of your computer science students are in courses where the students are trying to figure out what to do for projects, right? Or your computer science colleagues are wanting ideas to give students for projects. Creating an applet to simulate something, right? There are not good applets out there for simulating chi-square that I've found. Some, they're complicated, or they're either too complicated or they're too simple, especially for a nice goodness of fit problem, which a lot of our students in biology, a lot of our students in social sciences, anthropology, archaeology, things like that, they do a lot of goodness of fit kinds of tests. So I'd like to find or develop things to do that. Things that have multiple slots that have to be filled with numbers are difficult for hands-on, because you have to worry about your degrees of freedom too much. So what's next? There's probably stuff out there that's been made for science courses, economics courses, that we could use for probability and statistics. One of the issues, if you read the GAZE report, so when I say GAZE, is there anybody who's not familiar with that? The American Statistical Association, and then endorsed by the MAA and AMATIC. Basically suggestions for stat ed, and with a lot of data science programs popping up all over the place. Where and when do we start teaching students to program themselves? In all of our math classes, but in statistics or data science, data mining kinds of things particularly. And can students do that at the introductory level, or is that putting too much on them? Or what do we have to take out if we're going to spend time doing that? I'd want to find more hands-on, low-tech applets, either very simple computer things or things to play with in class. Most everything is dice and cards and maybe spinners, but maybe there are more creative things out there. And most of the applets are things where you set the parameters first, or there's a slider to change the parameters. The gamification I just do myself. You know, which team can get as many simulations done in the allotted time, or which team had more simulations which attained the goal of whatever the hypotheses were. But are there more game-like things out there, or could we use games that are out there, games that are free to access, and turn them into learning applets? That takes a little more time, because you have to figure out the probabilities in the game, which a lot of the game designers don't want you to figure out because they don't want, they would consider that a cheat. But if you could figure out the probabilities or have your students estimate the probabilities of winning under certain circumstances in some games, then the next step would be you could send your students out to find their own games or create their own games. Anything to make this course less like it looked in the 80s and early 90s and less like a lot of them still look. Calculate something using a formula, a t-score or a z-score, and look up a probability on a table. It sounds horrible that I'm still saying that, but that's how a lot of statistics is being taught in math departments and in schools of education and schools of health science and things like that. The course still looks like it did when I took it 35 years ago. So we need to find a way to change it. I welcome questions, comments. I would love to start writing some guided discovery activities that look a little more formal. So anyone who wants to work on that, let's get to it. I guess, John, if you want to unmute people. I'd love that people are posting links to other things, dice rolling and game things. That's really cool that we're seeing all that come up in the chat.
Yeah, so I mean, I can unmute people, or they everyone can unmute themselves if you would like, or just put in the chat if you would like, and I wouldn't mind reading it out loud if that would help. But I will say that one thing that comes to my mind, or a couple of things about just about how things haven't changed in so long. Is that in my department there are a couple of challenges, and one of them is that the online statistics classes are only 8 weeks and not 16 like all the on-campus classes. And so some of the students in the online classes have told us in the past, when we had more guided learning, that they just could not do it in the time constraints of 8 weeks. And then we have the other issue of the departmental final exam. And so right now we're at a situation where we actually finally agreed on rewriting the departmental final exam so that students could get the answers using a table or a TI-84, so that it wouldn't matter how the instructor taught it, they could get either of the answers. But I don't think that we're close to getting a majority of the instructors to teach by using applets and simulation. So I use them in my own classes, but I think that I personally think that those are some of the challenges that a lot of people are facing, like time constraints and other departmental constraints.
Yeah. I know when we met as a state to talk about state objectives for the intro stat course, we stopped writing objectives after 2 sample tests because we found some people were stopping there because they felt they didn't have time to go further. Some people went deeper into inference on regression. Some people did more chi-square, and in chi-square, there's a variety of directions you can go. Some people did ANOVA. Some of my colleagues who teach at regional universities in more rural Oklahoma have a lot of ag students. Ag research does a lot of ANOVA because they put a lot, they'll put 4 different treatments on large plots of land. And so they wanted to do that. So we stopped at 2 sample and said, this is the minimum to make the course transferable. And to be honest, if you think about it, what are students going to take from an intro course? You know, 1 week, 2 weeks out of the course, are they going to remember all the details of running a chi-square test of independence? No. But as I promised my students later on, when they take that research methods in blank course or quantitative analysis in whatever discipline, and they come back and they get more detailed into the types of statistical analysis that their field does, I want them to think back and remember big concepts. Right? What are we really measuring when we calculate a p-value? What are we really measuring with a confidence interval? When can we make certain conclusions about cause and effect? When shouldn't we? What should we watch out for when we're looking at assumptions? What should we look out for introducing bias, either purposefully or accidentally, into our study? Those big things are the things they're going to remember from an intro course, not the details of calculating stuff. So, you know, in that vein, you know, cutting back on the litany of tests, right? I can't cover every single type of data I'm going to collect in an intro course. I'd rather spend time on fewer tests and talk more conceptually with my students and get them understanding and communicating. And I typed this in the chat, but our college made the decision and we've been moving towards it. Starting this fall, we don't have 16-week semesters anymore, with only a few exceptions. There are some courses with long projects, like our film and video study program. They petition for 16-week courses, but everything else is 8 weeks. So our college year basically looks like 5 8-week terms, 2 in the fall, 2 in the spring, and 1 in the summer, with some 2 and 3 week intercessions built in around those for some courses. Yep, that's where we're going. And we're dealing with the same issues. But that's what we're doing. What else? I appreciate everyone coming. I see some other people have had to drop off and go on and go. I appreciate you coming and being willing to play, especially, rather than having to listen to me talk for an hour and a half.
Yep. Yeah. I am going to stop the recording anyway now.